Now we come to an interesting part of the discussion in this course, which is the measurement. The measurement, in a nutshell, is something that where we convert the quantum state and the information stored in the quantum states to classical information that we can comprehend and understand. And the measurements typically they collapse the quantum state, the superposition, and the entanglement they destroy a superposition, and then the wave function or the state is collapsed and becoming deterministic and classical. So let's have a look on the following example. We can have two-qubit system, Q0 and Q1. Then we act with a Hadamard gate here. So let's have the following example. We have two-qubit system, Q0 and the Q1, and these are initialized in the ground state. So if we have a look here, make a barrier, this is the state. Now we act with a Hadamard gate on the first qubit and X gate on the second. So the Hilbert space here is actually 1, 0, 0, 0 in this situation. So if we label the state, we have ket 0, 0, we have ket 0, 1, we have ket 1, 0, and we have ket 1, 1. Then first we act with H. So then we have H acting on the first qubit. So let's remove this now so we can see the action. So we can assume we have identity here because we don't do anything to the second qubit. If we do that, then H tensor I act on 0, 0. This would give us a superposition for the first qubit. So this first qubit will be in a superposition. So as a result, we're going to have 1 over root square of 2 ket 0, 0 plus 1 over root square of 2 ket 1, 0. Now let's act with the X gate. So and then since we don't do anything to the first, we can put identity and then identity tensor X or O times X acting on the new state. This will give us, so the X acts on the second qubit. So the second qubit then will be flipped. Okay, so what happens if we measure? We have here our Hilbert space now has two situations. We have one, we have here 0, we have 1 over root square of 2, we have 0, and we have 1 over root square of 2. This is corresponding to 0, 0, 0, 1, 1, 0, 1, 1. So what will happen here? Each coefficient will be corresponding to the probability or what I will find after the measurement. So when I do the measurement, the superposition will collapse and then I will have classical state. The classical state will be one of these, then one of these will remain. So this situation, I won't find it. This one is possible because it has some coefficient. There is some overlap. This one is not possible and this one is possible. And this is why my state now, I will have it to be, let's make them with primes to distinguish that this is a final state, would be 1 over root square of 2, 0, 1, and 1 over root square of 2, 1, 1. So we have two probable situations here. When we do the measurements, one of these situations will remain and the second will vanish. And hence, we have two situations. Either the first qubit is 0, the second qubit is 1, or two qubits are in one state. So in that sense, when we perform the measurement in our circuits, we put here, we have Hadamard, we have X, then we make a measurement in Z, which is the computational basis, then we either get 0 or 1. However, the second, for sure, we are going to get 1 in any situation because it's only has 1. So the two situations contain the second to be 1. So in that sense, I will have two digits. Either the first is 0 or, so I have two outcomes. Either the first is 0, second is 1, or the first is 1 and the second is 1. This is the second outcome. These are two digital numbers, so I need the classical register to retrieve them. So I use two classical bits to retrieve those. If we back to the presentation, we see an example like this. We retrieve the numbers like this. We can have a situation where Q0 is in 0, Q1 is in 1. So the measurement operation will collapse the superposition of the qubit into classical state, and then the measurement results are stored in the classical register. And this is an instance of this example. So this is a quantum measurement that we can have. So when we perform the measurement, we are collapsing the quantum state to one of these probable situations or configurations. We have to make a clear distinction between the classical superposition and the quantum superposition. The classical superposition, you can impose or you can add things together so they can reinforce one another, like the interference of water waves, sound waves, and so on. In quantum, it's different. It means that we have simultaneous existing of several distinguished situations, which when you measure, this situation will disappear except one situation will appear. So one situation only will be remaining. And this is, in our case, could be a situation where the first qubit is 0, the second qubit is 1, and then we have 2 digits to retrieve from the measurement. And mathematically, the probability of obtaining a measurement result is given by the Born's rule, which is the p of the measurement result is a square of this coefficient in the way that we have seen it, the complex conjugate of the number times the number. So that gives the modulus squared of this number. So the probability to find the qubit q0, q1 in the state ket 0, 0 is given by this square of the 1 over root square of 2. So we get half. And then if this we assuming we have applied the Hadamard gate only. And if we have the probability to find the 2 qubits in the state 0, 1 is 0 because we have nothing. The probability to find the qubits q0, q1 in ket 1, 0 is half. And the probability to find both of them in 1, 1 is 0. So this is only happens after the Hadamard gate. So if we have the 2 qubits here, I have a Hadamard. This is my state vector, 1, 0, 0, 0. And this is after applying the Hadamard, I have 0, 0. So I have here the two numbers, so the probability of finding the 2 qubit in where both of them are 0. This means that I obtain the situation where both of them are zeros. This will equal to 1 over root square of 2, the square of this number, which is half. Then the probability to find ket 0, 1 is 0. The probability to find first qubit is 1 and the second is 0. So the situation 1, 0, that will be the square of 1 over root square of 2 squared. And then the probability to find both of them ones, that will equal to 0. Okay, so from these coefficients, we can retrieve the probabilities. So you see there is some deterministic pattern over the probabilistic nature and the statistical nature of quantum mechanics, that you can still predict the coefficients and predict the states with certain probability. So if you do or you perform the experiments many, many times, you get this by probability. How many of these times you are going to find both of them zeros, and how many of times you are going to find them, the first one is 1 and the second one is 0. And since we got half, it means that we get 50% of the time the first state and 50% of the time the third state ket 1, 0.